In this video, I'm going to talk about cross-validation methods. In the previous videos, we discussed goodness of fit measures, such as standard error of the estimate, R-square, and adjusted R-square. All summarize how well the sample regression equation fits the data in linear regression models. And in binary choice models, we use accuracy rates to measure the performance of logistic regression and linear probability model. All these measures that we have learned help us assess predictability in the sample data that was also used to build the model. Unfortunately, these measures do not help us to gauge how well an estimated model will predict in an unseen sample. So now I want to talk about the problem of overfitting. It's possible for a model to perform really well with the dataset used for estimation, but then perform miserably once a new dataset is used. And if you remember that in linear regression models, you can easily improve the fit as measured by R-square by adding more predictor variables. You can add one more here, and one more here, and then R-square is going to increase. But these predictor variables that you had may not have any economic justification. We often call modeling of this sort overfitting. So when does overfitting happen? Overfitting occurs when a regression model is made overly complex to fit the quirks of given sample data. To prevent overfitting problem, we use cross-validation techniques. Cross-validation is a technique that evaluates predictive models by partitioning the original sample into a training set and a validation set. So in cross-validation, what we do is, this is our sample data, and we divide the sample data into two partitions. The first one is training set, and the other one is validation set. So the training set, let's say you partition this much and you include this variable. You built your model or models. You might have more than one model. Let's say model 1, model 2, and model 3. And in validation set, you don't build any models. You are going to test the predictive power of each model in the validation set. Therefore, a validation set is used to provide an independent performance assessment by exposing the model to unseen data. Root mean square error, as you see here, is equal to, in square root, summation sign, in the parentheses there is y minus y hat, and then square divided by n star. Recall that y minus y hat is the residual. So you are calculating error for each observation. So you have a y, actual data or response variable, and you predict one response variable, and you take the difference for each observation. Then you square these differences for each observation. So you'll have a column of squares. And then you sum all these squared differences and divide by n star. N star is the number of observations in the validation set. Therefore, root mean square error is calculated for the validation data set. And then you take the square root. So what we do, let me repeat here. You are going to, let's say, build 3 models, M1, M2, and M3 using the training dataset. And then you are going to predict y hats, y hat 1, y hat 2, and y hat 3 using 3 models. And then you are going to calculate root mean square error for each model. In the validation set. And one important point is that root mean square error will be lower for the training set than the validation set. The reason is because we built the model in the training data set. We expect that the model fits better to the training data set. So how do we decide which model is the best? The general rule is that A large discrepancy between root mean square error of the training and validation sets is indicative of the overfitting problem. So that means the model fits the training dataset very well but fails to generalize to an unseen dataset. And if you have a binary choice model like logistic regression or linear probability model, you are going to use accuracy rate for validation set. That means root mean square error is for linear regression and accuracy rates are for binary choice models. Now let's talk about holdout method. The simplest of the cross-validation methods is the holdout method. The sample data is divided into two partitions, and these partitions are independent and mutually exclusive. So the first partition is training set and the second partition is validation set. For illustration purposes, we will use first 75% of the observations for the training set. 75% of observation for training and 25 remaining is for validation. The holdout method is implemented as follows. First, partition the sample into two parts, training and validation. Then use the training set to estimate competing models. And then use the estimates from the training set to predict the response in the validation set. Calculate root mean square error for linear regression models or accuracy rate for each competing model. The preferred model will have the smallest root mean square error or highest accuracy rate. Ideally, we would like the model with the best performance in the training set that we measured by adjusted R-square also have the best performance in the validation set. For example, we would like that the linear regression model with the highest adjusted R-square also have the lowest root mean square error in the validation dataset. And if you find conflicting results between the two, then you may have the problem of overfitting. After selecting the best model, we generally re-estimate this model with the entire dataset for making predictions.